Okay, so there's 4 newtons of total force on here. The system is being pulled to the right at a horizontal frictionless surface by a horizontal force of 4 newtons. Both blocks experiencing equal constant acceleration. If they're both experiencing equal acceleration, right? So if A of 2 equals A of 8, then that obviously means the system is in equilibrium, right? Because when you first pulled it, like, does it make sense to like the spring would stretch and da, da, da. But then at some point that stops and now it's just moving there. So we know that like whatever the sum of the forces, like the total force is equal to the force on 2 plus the force on 8, right? And then this is like the total mass times acceleration, which equals the mass of 2 times A of 2, which equals the mass of 8. Well, I know it's 8, but you get what I mean, right? But then from this, since we know that the accelerations are the same for all of them, like, you know, everything's in equilibrium. Does that make sense? You don't have to write that down. I'm just kind of talking us through the problem. All right, so then the force exerted then, it's just a matter of proportion, right? So if there's a total of 4, how many times bigger is this than that? 4, right? Do you see it? So there must be 4 times as much force on this one as there is on this one, if they're going at the same acceleration. What's that? Yeah, it would be by 5, right? So it's like 0.8. Remember we did this with circuits or something like that? Like, we did proportional circuits, remember? So it's like if this is 4 times bigger than this, then the trick you use for proportions is you say if one of them's 4 times bigger than the other one, then that gives you 5 total units. So take the total, 4, divided by 5, and that's 0.8. So then this gets 1.6 newtons, and this gets 2. No, that's not right. Wait, let me mess up. I see. All right. This. So this is 2. Jeez, for some reason I multiplied by 2. I don't know why I did that. Sure. Like, well, let's see. What is a way to do this? Oh, you could go. I'm not sure how to do this mathematically. Well, okay. Just written here. I would say something like, to determine proportions, I just take everything and divide it by mt. How do I do equals? Right? And then from this, you can see like this, that's like 1, this is 1/4, and then this is 3/4. What's the total? It's 10. See, that only comes out to be 1/4. Sorry, my brain got sidetracked. Yeah, so we have 4 newtons of force, right? And it equals m2a plus m8a, right? So you just calculate. Oh, so what is that, 0.4 meters per second squared? And then so you get the acceleration. Was that what we're looking for, the acceleration? Oh, the force. So the force on 2 is equal to the mass of 2 times a. So then that gives you 0.8 newtons. All right, the next part is B. Calculate the extension of the spring. Okay, so you know that if everything's stable, right, if we draw our force diagrams, right, something like this, and then here, the sum of the forces on 2 is going to equal m2 times the acceleration, right? And the only force is the force of the spring. True? There's nothing else pushing it. So I know the force of the spring is M2A. Okay, and then what do I know about Hooke's law? Yeah, I'm just going to say Kx because I'm orienting it in my head. Did they tell us the spring constant? Oh, good. I was like, oh, crap. Am I supposed to figure that out by some clever hijinks? No, that's good. We don't have to be clever. We just have to be consistent. And so we get 0.8 divided by 80, which comes out to be 1 centimeter or something. No, 0.8 divided by 8 would be 0.1. Yeah, 0.01. Sorry, he says, is the magnitude of the acceleration greater than, less than, or... Oh, okay. The system's now pulled to the left as shown, with both blocks again experiencing equal constant acceleration. Is the magnitude of the acceleration greater, less than, or equal to the